So after all what the theory hold, the viability theory, optimal control theory, I mean the hard equations showed. Now I will turn up to show you more of the applications, what people have done, what people use as tools to show some models, some interesting results, and it can be differentiated in three stages. First of all, I will show one of my early applications I studied on, which is fishery management. I will explain how it works, etc. Second of all, I will explain one of the recent applications people work on, which is epidemiology, and how much we can work on in the current cases. And actually, now in 2022, we can also work on this field. And later on, I will give you a more general but also specific case of how we're gonna use the optimal control theory and those hard equations, how they're gonna transform and become an easier one to study. So I become the fishery management with introducing you to what we call the fundamental fishery model. I mean, when you see fundamental, meaning it's the early one possible. And I think this model was made in the 60s, 1960s, which is meaning the variation of x. Let's say x is the stock of a stock of a fish, meaning like sardines or some kind of fish you love. F he signify the growth function of this stock. Either it's an increasing growth function, a decreasing growth function, a constant growth function. You choose whatever you want. It's your model, to be honest. Minus that, we're gonna take what we call a production function. You're gonna see the multiplication of q, a factor, multiplied by two variables, x and e. X here signify also your stock, and e here is called what we call in fishery management the fishing effort. And QXE is what will also known in literature as Cope-Douglas production function, is the multiplication of the two state that you have, and also known as the production or the competitive actions. I will show you later on how it works. Whenever you have competition, it's the multiplication of one variable with another one factor, another variable, another constant or variable. And here you see the efficient effort. The E need to be between 0 and E maximum. You're gonna start to think that this is a dynamical one. So you can see that E could be seen as a control variable. You're gonna control E to satisfy that the stock of fish need to be in some kind of set. And here you have lower, E should be bigger than 0 and E maximum should be 0. For example, just imagine if E equal to 0, meaning you don't have the QXE, meaning that the function is easier to study. It's just the integral of fx, meaning that your whole function becomes just the growth function. Derivative becomes just the growth function, and that's easy. And now let's see the problematic. So what's the problematic? The problematic is maximizing, easiest, is maximizing the integral of between 0 and infinity, the exponential of minus delta t. This is an economic thing. P minus c qx multiplied by fx minus x dot. Here you're gonna, this has been taken off from this function because here you need to see that it's not always the function. And this is the problematic. This take us to what we all know, either the optimal control theory, you're gonna study it so fast, or you're gonna use what's known to be known as the calculus variation. You're gonna have an Euler equations that give you the following. So everyone should know that in the 1960s, this model has been used mathematically, control model has been used mathematically to save the whales in the US and Canada shores from being extinct. So this model has in the 60s worked to save the whales of the Canada side, the Canadian side and the US side. And after that, people thought about this model and how they can make it more realistic to just continue with time and just get improved. So in 1979, there is three people here. You're gonna understand them. There is Colin Wellcome Clark. There's also Francis Clark. For those who know Professor Ludovic Riffard, Francis Clark is his professor or director de thèse, and Gordon Moreau, which is one of the economists, the better economists of the Canadian economics ever. And they had an article called The Optimal Exploitation of Renewable Resource Stock. And actually, what they did in 1907 is they had a problem of maximizing a profit, which is mean like you see here. There's the profit, meaning they PQEX minus CE minus PE. It's a profit function with respect to now a two-state variable, meaning they have X as a state and K as a state. They have two-state variable, and you're gonna see here that they have a unique thing as a control. They have the E as a control, and this time, as before, they take the investment as non-bounded value. They can be between 0 plus, it's bounded but just lowly bounded. It can go from 0 to infinity, and infinity included. And actually, this was one of the most revolutionary, and it did revolutionize the way of thinking of the investment, because they said that the cases when ET equal to infinity allows us for instantaneous jump in the level of capital. By doing the optimal control theory and the whole gibberish surrounding it, they found the following graph, more easy to study. So they found that for any stock coefficient, for any capital level, just to compare the two, you can think the stock coefficient as, for example, the sardines in Morocco or the sardines in the Mediterranean Sea or the Atlantic Sea, and you're gonna think of the capital as the boats available for that activity. For example, by having like a lot of money, you're gonna have a lot of boats, then you're supposed to catch a lot of sardines. So what they said is when the biomass, they have divided this set into three different regions. When the biomass, meaning the available fishing levels are low, you can see here, when the available fishing level are low, you should not invest, because by investing you will have a lot of boats, and these boats will not work efficiently, meaning you will lose money on gasoline, money on people working on that field, so you will lose money, so you should not invest at all. And when you are in the middle region R2, this is the region of sustainability of the activity. As you can see that all arrows are directed to this region. You can see them. These are the arrows directed to this region. So by this region, it's called the region of hard work, meaning that you will try to maximize, you try to utilize your whole capital without investing, meaning that if you have 20 boats available, you will take the whole 20 boats to the fishing activities. You should do anything just to fish at maximum. And on the third region, the region where it's completely insane what they said they need to do, when there is an abundance of stock level, meaning like for example you found a lot of stock of fishing, what you need to invest infinity. What does it mean invest infinitely? Meaning you're gonna do what we call a surplus in capital, meaning someone will come and just throw money at this activity. It will, like for example, we will be in a point here. What will happen is that we will be jump until we reach this curve, which is sigma 2. By reaching this curve sigma 2, you're gonna change your policy from E plus infinity to the R2 activity, and then you will slowly follow sigma 2 until you reach the point B, and then you will go here to the middle, because everything will push you this way. So you go into the middle between C and B, and everything will be like pushing you to stay in the middle. So here they found that this activity actually make them win money, and these control policies make you win money and also save a lot of fishing stock. because one of the things that you should see when you are in the region R1, not only you do not invest, but your also fishing effort is zero. Meaning, this is what many people call the biological rest. Meaning, the government say you should not fish on those. It's the biological rest. We need to let the stock rebuild. Meaning, you should wait until your X reach a level between here, then you should have an activity. And this one was one of the, if I should be saying this out loud, this has been a revolution to people thinking, and this has made so many ideas about how we're gonna do fishing activities and how much it impacted the world, that until recently people used this politics to invest and to do fishing activities worldwide. But now I've spoke about the optimal control theory. How about the viability theory? Meaning where you don't have any function to maximize, We don't have these things. And I will have a model that's similar to the last one, but this model will be explained in more detail. We have two state variables. For example, let's go always with X being, since we are in fishery management, let's go with X being a stock of fishing. It has a growth. This is the growth function. It's a logistic function, and QXE stays the same. Now let's have a second variable, a state variable, and this variable should be called the price of the stock level, meaning how much you'll be selling these stock fishing to the people. And the stock is a difference of demand and an offer and demand, and you have it's the difference between demand and offer, and you have here the demand of the will dependent to the price minus the offer, meaning how much we take, how much we fish, which is QXE. And here you're gonna see that we have the control function as ET. So we have two state variable and one control variable, and the control will be the fishing effort, ET. And here we will assume that the fishing effort should be always between E minimum and E maximum. We will avoid the cases which say not to fish because it's not very intuitive. When you stop fishing, meaning you will not have how I'm gonna say this out loud. By not fishing, what it will call out to the price of that fishing stock will rise to infinity. Meaning it's not possible, almost not possible. This is what we call the surplus, or how much should I explain it also, is when something is not on the market, its price will rise up. When it's always in the market, its price will rise down. And this is what it's called, why we will avoid E equal to 0, because by getting E equal to 0, it will shoot up the price to infinity or a higher value, and this is not very realistic, to be honest. I can later on give you reference to this work, but we can find what we call the viability kernel using only economic constraints, meaning only using ET between E minimum and E maximum. And we're gonna now tell you what's these economy constraints be. So we're gonna choose to have the price between a lower value P and P dash in the low and P bar as the maximum price. And here you're gonna see that we need to guarantee a consumption level throughout time with P bar and P dash to guarantee a global positive net benefit in the sector. Meaning that we should not sell the fishing stock at loss, meaning we should gain money. And also P bar, we should not sell it to make people scared of those fishing stocks. You just should imagine if the sardines do have lower price, everyone will buy them. If they have an extraordinary high prices, no one will buy them, meaning everyone will think they're expensive. Why buying them? And we will try to avoid both cases. And yeah, now it's seeing how the viable stationary point, meaning we're gonna just do the stationary point, meaning put in x, the derivative with x with respect to time equal to 0, the derivative of p with respect to time equal to 0. It will give us two isoclines. The intersection is what we call the viable stationary point or the stationary point. Here it's viable if and only if it verifies the two conditions, the two hypotheses, h0 and h1. h0 say that the heats should be logical, but the growth of the fission stock, meaning the growth of the fission stock, should be bigger than how much we're gonna catch at a maximum level, meaning that in no time possible we will be efficient stock more than what it could rebuild, meaning that we always have a sustainable activity. For example, if the fishing stock double each day, we will force us to not fish more than double each day, making that there will be stay parents to give birth to others to make the life cycle continue. The second hypothesis is with respect to the demand. We suppose that when price goes to infinity, the demand goes to 0. So we have a price that is unique, and when price goes to 0, the demand goes to infinity. This is a way of thinking of demand. When something is a lot expensive, the demand is lower. When something is very cheap, the demand is absolutely enormous on it. And we're gonna find the following cases for the viability kernel. You'll find the case where the viability kernel is a empty set. It's a cool set. We also will find cases where the viability kernel is not an empty set, and we actually will find that with certain condition, which is h0 and h1, and also the fact that w is not empty, meaning there exists a viable stationary point there, that what you see in the red are the bounds of the viability kernel. So the viability kernel is everything that it is inside those red lines that is forced with two curves L1 and L2 in these two lines. This is the viability kernel. What's possibly can we understand? For example, we're gonna have here two different prices points. We have like this P dash and P dash here. Just imagine for once what happens when the price is a lot larger. Like here, you know that when it's more than this price, nothing will survive. When it's lower than this price, nothing will survive. Even though we are in this set of constraints, just think of it when you have lower value of stock but higher price, it's also not viable, meaning that you will cause a lot damage in society. So what's inside here is all the initial state from where we can always stay in this activity. And this work has been used, I guess, in Morocco, to be honest, to just monitor the pricing of the fishing stocks in some way. But now it will be the end of the transitioning from fishery management. I can, after this sessions, give you many articles about it, even my own article where I use the viability theory in the same models. And now I will transform to more simple application about epidemiology that everyone should get interested to. So one of the questions that rise, how math can help us fight infectious diseases. What do we mean about infectious diseases? We mean like COVID, pox. Now everyone knows there is the monkey pox. There was always something that is called chicken pox, Ebola, flu, all those diseases that are transmitted called infectious diseases. And how it works in a simple way. I'm going to show you a simple way how it works. It's called the SIR model. The SIR stand for susceptible, infectious, and R meaning immune, or someone who has not has gone up from not being susceptible or infectious, but has survived these diseases and developed some kind of immunity. And you're gonna see that there is like people who are susceptible. Some of them might get infectious, some of them might not. And those that get infected, some of them will develop an immunity. Some of them might die, some of them might not develop an immunity and become also susceptible once again. And this is how it help us. It help us, as everyone knows, it will help us predict what everyone calls COVID waves, in a more cases to be understand. And by studying the dynamic, you will see that the susceptible cases, the people who are susceptible to get the disease, will be a decrease in function. From 100%, it will decrease because people will get infected with this disease, So the susceptible number will get lower. What happened is that the people who develop immunity to it will rise because people will get sick. And the infectious and the people who are infected also will rise. But there is a point where it will go rise up, then it will rise down, and this is what everyone calls the first wave, the second wave. And I guess many people have heard of you. Now we will enter in the fourth wave, the COVID virus, the third wave, the COVID virus. And actually that is just waves of the infectious cases going up and going down, meaning that what happens is when the immune people are lower than the susceptible people, then you will bound to have again a kind of relapse and a kind of a wave. And this is work in almost all epidemiology disease cases, but mainly in the SIR model, meaning susceptible, immune, and some recovered cases. COVID cases, early in 2019 when COVID started, people used this SIR model. Now we are in more complex usage of SIR model. It's more complex than SIR. I guess, yeah. Here's a new case of more complex SIR model. It's from COVID modeling, and it's more complex. You'll see that there is the S, there's the I, and there is the R, so it's staying SIR model. But now there is like a lot of new cases, meaning that people who are susceptible might get sick here, meaning get sick and not need to go to the hospital. Some of them will need to go to the hospital. Some of these people will just go out from the hospital. Some of them will die. Some of them will develop no immunity and also become susceptible. And you see that there is an intricate, complex side between all cases. And this is a controlled, optimal controlled model. The control here was the alpha T, alpha T, eta T, and I guess tau T. There's all different kind of control policies, either through quarantine, QT meaning people that are in quarantine, also through television, people doing things on television, meaning a lot of control policies. And what we saw on the exposed in the infected people, and that dependent on which kind of trend or policy we're gonna make. Some kind of policies, as you mentioned, had public health education, quarantine, and isolation. It's the dotted red line. You're gonna see that the exposed individual is low, and one day it will shoot up. It's the same with the infected people. It will be low, and one day it will shoot up. What we understood about this, because one day the quarantine will end. One day people will stop being isolated, and one day people will just get done with the education and just to get done with everything. So one day it will shoot up. The black line is actually just X's, would mean we just do double control, meaning public health education isolation. Public health education isolation mean that we will do control policies over public education, meaning teach kids in school, do ads on TV, a lot of these things in isolation, meaning people who got sick on the hospitals are being isolated, and also people who get sick are isolated. But we will not do quarantine, meaning stop everyone from living. And you're gonna see that what's happened is that cases will go always up, 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 and then shoot up one day. This is how much exposure. What happened is that infected, it's gonna be decreasing because first of all it will be rush up, and then it will be slightly continuously increasing, then it will shoot up at last time, and vice versa depending on other policies, meaning quarantine isolation it's in the blue, and public health education and quarantine is the one with the lowest one. Some people, it depends on, like for example, if I give you the choice of which thing you gotta choose, it depends on you. Some of you will tell me, look, I'm more about doing one thing and one thing only, and here it depends on the strategies of each country. Some people trying to lower the number of exposures, some are trying to lower the number of affected individuals, and these two are, I mean, not very the same, because you can see that the blue heat is a lot bigger than the dark heat, and are not the same. So it depends on the strategies of each country, and even you give them all the possibilities. Now I'm gonna change more into the epidemiology, but into more of a different kind of models. The model that I'm gonna present to you is the cancer modeling. And yeah, math can save life. Math can save cancer patient and can do patient cancer treatment. And this is one of the models made by a student that was with me in her PhD. And her model was very simple. It was just trying to minimize function. T here mean the not the cancer, the tumor cells, and C here is what they call the chemotherapy doses. And you know that the chemotherapy is also bad for the normal cells. And here it was two-dimensional model. It was the tumor model, meaning that it has a growth. It died because of her fight with the CT, meaning it died with her fight with the chemotherapy, and also it died with its fight with the with the effector cells. The effector cells is our immune system. What happened is with the immune system problem is very difficult. The immune system, we start with a number. I mean, we start with a number of immune cells. What happened is that they will decrease with respect to time. When we were younger, we have lower cell. We got lower cells. You can see this. Older people get sick easily, meaning the immune system become weaker because the immunity goes down with time. However, it gains some little bit of confidence by fighting the tumor cells. Fighting tumor cells, we understood by looking to data that fighting tumors get your immune system more knowledgeable with the tumor cells, and now he can fight them efficiently. However, with each battle, you will lose some kind of fighters, and you will lose cells with respect to their fight with the tumor cells. And also, what you should know about chemotherapy, chemotherapy is deadly, meaning that it does not only kill the tumor cells, it kills every cell. That's why you're gonna see that people who get cancer and choose to go through the chemotherapy, they lose their hair, meaning that the cells, the chemotherapy start attacking cells that produce hair. They become weaker, they become pale, meaning that chemotherapy does not only attack one kind of cell. Chemotherapy is deadly as it attacks everything. This is why chemotherapy is the worst way to fight cancer, but also the best way to fight cancer. I don't know how to explain it. This is why we are more interested into finding the best way of minimizing the effect of chemotherapy on a patient, but also maximizing uh, minimizing their side effect, but maximizing its way of killing those tumor cells. And this is how we're gonna model this problem. You're gonna see that the chemotherapy was the control problem here, and the this was the objective function. And throughout time, what we notice is that choosing a policy, which is the following, meaning having a chemotherapy doses for the first 4 days, and then to stop, wait for the time to rebuild. What it gives us? It gives us the following result. The tumor will start dying, and will continue dead. Why this? But you can see also that the effector cell, mean our immune system, what happens to them? They also die. But they rebuild a bit, but they also stay here. See, this is why I tell you that cancers is very difficult. Don't mention that what you're gonna see here, there is like, here it's not zero, it's more than zero. We cannot eradicate cancer. This is something you should all know. It's something that I was scared to know from doctors, that we all have cancer. We all have cancer, and a level above what we call the minimum threshold is then when you're having what we call cancerous disease, and your tumor need to be treated. Uh, and we cannot eradicate tumors. The problem, what happens is, if we continue in time, what happens if the tumor can rebuild, and this can be relapse. Some people fight tumors and fight cancers, and you're gonna hear that they need to always go to the doctor to check. It's becomes as 6 month check, 3 month, 6 month, 1 year, and when we see that the tumor is not rebuilding, we make this gap bigger. But we can have relapse, meaning that someone who fought a tumor, who got better from that tumor, is not in the cancerous type, the tumor can rebuild and reach also a level. The problem here is, you should also try to eradicate T, meaning try to give it a lower level of T, but try also to not kill too much E. Try to not kill too much the immune system. And this is something I should tell you. A lot of people, a lot of people, this is, I don't know if I should say this, but I will say it out loud. A lot of people, what we notice on diseases as cancer, a lot of people don't die because of their tumor. They die because their immune system isn't strong enough to fight other diseases than the tumor. Some people die of flu. Some people die of infection, just because by doing the chemotherapy, their immune system gets so low that anything can break them down. And the problem is, we cannot give them injection of anything as to help them with the effector cells. But this is just, as you can see, this is the chemotherapy. Now there is also the immunotherapy. There's another type of how we're gonna treat cancer. It's trying to boost the immune system by trying to boost the effector cells, trying to cheat it, and type of cheating, to be honest. But this is not the case today, so I'll not show you that. And this is a good way to transition to a more novel case, a more interesting now case. It's our third application, and it's the application on waste management. How it's now gonna happen is, I'm gonna try now, as you see on the first two applications, I'll show you the models, and I show you the result, and try to interpret the result, and try to how I'm gonna explain to you the things that go in it, but not in details. Now I'll try to just show you cases an application, but also try to show you the mathematical behind it, the mathematical tools behind it. Meaning that everything I showed on the control optimal theory, those equations, I will show you now how they look like. So, this was an article published in 2021. It's about building a bioeconomic model that describing an investor who want to make money by transforming waste into energy. This is something that is very recent. It's something that now people are leaning to because of climate change and the abundance need of energy, because now we need to understand that energy cannot always come from fossil energy, meaning petrol or gas or a lot of things. It needs just to we need to have another use of where we can get energy. And also the second problem we're gonna face is try to convince this investor about the profitability of this activity. So how it works? It works just we're gonna take a simple model, just a simple way of thinking. We're gonna take a bus or some waste, and you're gonna put it on what we call here the waste stock, or we call it the landfill. You're gonna take some of these waste to put them in these processing unit, and they're gonna generate to you some energy. But you should understand that these processing units are not built with nothing. They build with money, meaning they build through investment. So this is our first control variable, investment. How much investment are we gonna make on this activity? Second of all, how much waste we're gonna take from the landfill and put in this processing unit. You're gonna be saying, I'm gonna put all the waste, but what happened tomorrow if you don't have any waste? You're gonna stop the work, meaning you're gonna pay people for not working. This is good for us because I guess some people are lazy like me, they like to get paid by not working. But for someone who's investing money on a business, when you're telling him you're gonna pay people for doing nothing, he will just be mad and not liking that idea. So we need to choose a ratio of waste that's we're gonna put in the processing unit. QT here is a ratio, so it's just between 0 and 100%, saying that we're gonna take 20% of waste and throw it on the processing unit, or take 100% of waste and throw it into the processing unit. And the model is like this. It's a very simple model with a type of with a bit of difficulties in some way. So the model in equations, it's a three-dimensional variable. The model, the first variable x is the waste levels. So we get a constant flow of waste, which is omega, and we get a biodegradation rate plus qt by x. We produce energy by putting waste into the processing unit, okay? And also the energy is depreciated with time, because everything depreciates with time. And the capital here is equal to E minus gamma K. This is how much capital increases with all the investment we make, but we lose this investment throughout the time, meaning that anything economic lose value on time, meaning that we will lose gamma K. As I mentioned, if you remember above on the introduction, one of the first things we try to understand is how much the stability of the model and the component act with each other. So here we're gonna see how much the component of this model react to each other, meaning the equilibrium, how they are, how much they vary, how much the influence of a variable with another one. So we understood that we are in a case that is super beautiful. We are in a case that exists a unique solution, meaning just one solution that's perfect, and the solution is globally asymptotically stable. It's another way to say exponentially stable, meaning it will have a rapid, it will go speed with the top-notch speed to the equilibrium. It will go faster to the equilibrium than a normal stability one. And now we're gonna see how much we're gonna learn from this dynamical study to go to the more of control policy. So in order to maximize the net profit generated by the sale of this energy, the decision maker might choose both the ratio of waste to be transformed and the investment policy. So we should always keep that in mind. And also introducing the problem to investor who seek to maximize the income generated by the sale of this energy that he produced via the described process. So the problem became this holy one. So we have a time t, which is the finite time horizon, depending on the activity. I mean, normally, just between us, this activity or this investment activity takes between 25 years and 35 years. So it's not very long time, but not very short time. I mean, if when you're signing a contract, you're signing them for 25 or 35 years. That's a long time, but that's not infinity. So we will choose a finite horizon time for this activity. The energy is supposed to be sold at a given constant unit price P. Here we just choose to sell the energy at a constant price to avoid inflation, meaning when there is higher demand energy, the price will not go up, and when there is lower demand energy, the price will not go down. Just we will sell it at a constant price the whole time, just to avoid inflation in other prices. We'll also choose a given unit cost of production C and a quadratic investment cost. This is known in the literature as when you produce something, there is a linear cost for it, but when you try to invest in something, there is two costs. There is a linear cost, which is the production cost, and there is what we call the reinvestment. You invest on your investment, meaning like it's a double investment and you have a quadratic cost. And it becomes a maximization of the following problem. You sell the energy by price P, meaning you multiply P by E, then you take down the costs. So there is a cost of production, a unit cost of production C. So C multiplied by what we produce QT XT. So we take QT ratio from the waste XT. And also we invest E. So E is having a quadratic cost. So E C1 plus C2E with respect to also our system. So what happens now? What happens is that we noticed that the trend suggests by theoretical result a potential behavior of the control policy, meaning that this control policy E and QT, they have this following trend. The first one consists with no recovery of waste while a maximum investment is employed, meaning you start the activity by investing a lot of money on it, and by not doing anything, you're just gonna wait until you have enough money, enough experience, enough processing unit to start working. The second one is to recover at a maximum ratio, meaning you will work by transforming 100% of the waste all the day, and a decrease in investment, meaning now you will not invest as much as you used to be. And the later stage of the activity, meaning when you will reach the 30th year, when you are close to the end of the contract, what you're gonna do, the later stage is without any recovery, any investment, meaning in the later stage, what you're gonna do is you're gonna take an early retirement. You're not gonna invest anymore, you're not gonna work anymore, you're just gonna take your money and leave it. You're not gonna touch it. You're gonna win on your benefit. And how did we get this following result? And actually what we did is, first of all, we written the Hamiltonian function. The Hamiltonian function is the scalar product of the P, meaning what we call P is the co-state values, with the system, our system, which is the 16th equations, and we add to that the what we call the objective function, meaning the profit function, and it's as follows. So it's the profit function, which means the objective function, plus lambda 1 multiplied by the x dot, plus lambda 2 multiplied by e dot, plus lambda 3 multiplied by k dot. Here you're gonna see this is why we call them co-state, because each co-state is dependent on a state, meaning that lambda 1 is dependent on x, lambda 2 is dependent on e, lambda 3 is dependent on k. What happens is now we're going to use what we call the optimal control theory, or an adequate version of the Pontryagin maximal principle. So we have the lambda, which is lambda 1, lambda 2, lambda 3, and we have the four different equations. So I'm going to explain to you the four different equations. The 17 and the 18, if you don't mind, I will do a back and forth with what I did on the optimal control theory. So just remember the 17 and the 18, key T is the differential of the Hamiltonian with respect to the co-state, and lambda dot is the following. And by going to the optimal control theory, you're gonna find that those are the equation 5. P is lambda, so xt is the differential of h with respect to lambda, and P is minus the differential of h with respect to x. And by going back, you're gonna see that it's exactly the same one. Now, 19 is what we call the maximum principle. I guess everyone remember that. It's the maximum principle. Beautifully written. We remember it with the max. However, 20 is what we call the transversality condition. And now I will go back to show you what the transversality condition was written. So remember, there was the condition 7, which is called the transversality with respect to the Hamiltonian. This one was good. And also there is the transversality with respect to the co-state. Remember that we will have the first one and the second one, 8 and 9. However, in our case, we said that the finite time is fixed, meaning that m capital T, we know it. So we will 9 and 8 become almost the same. Why? Because you see here there is this differential with g with respect to time. G, if you don't remember it, is the integral plus the g function. In our case, the g doesn't exist, meaning that this differential with respect to time equal to 0, meaning that this becomes the maximum is equal to 0, and this will become this, and this will become 0, meaning p0 and pt are equal to 0. And going back, you're gonna find that it's just lambda capital T equal to 0, and h of everything capital T is equal to 0 too. And that's something we're gonna do after that. So everything is beautiful now, everything is simple. We're gonna use the equation number 18 to rewrite all the co-state variables to see them how they look. So we write the lambda 1, lambda 2, and lambda 3 differential equations, and we're gonna add to them the 20 equation, lambda capital T equal to 0. We'll have lambda 1 capital T equal to 0, etc., etc., etc. And this will help us solve all these differential equations. They're a bit hard, but you can see that we can solve the second one easily, as it doesn't depend on any other state. Lambda second depend only on lambda second and constants, so it gives us the following. So, well, we're gonna use the maximum principle. So according to the maximum principle, 19 lead to separate optimization with respect to each control. The first one is linear and the second one is quadratic on bounded state. Thus, the expression of the control is straightforward. The first one is the second control, which is E. I mean, the one that was quadratic, the one that we had E plus a factor, C1 plus C2E. So we had an E square on that. By deriving the Hamiltonian with respect to E, we had an E left, and this is where all of these things come. So ET, the investment, is a maximum investment whenever we have this inequation. It's 0 whenever we have this, and it's this one when it's in between. What happened with the other one? I mean Q. What happened is when we derive this Hamiltonian with respect to Q, we have only one Q, so it disappears. When it disappears, we will have the differential of the Hamiltonian with respect to Q equal to such function, phi t. And now this Vt, if it's positive, we're gonna state that the Hamiltonian should be equal to 1. When it's negative, we're gonna state that the Qt is gonna be negative. And also here, something that I should state, the existence of a singular solution is excluded because of the necessary condition. A singular condition is what happens when Vt equal to 0, because here you consider that Vt is positive, strictly positive, Vt is strictly negative. What happens when it's equal to 0, in between times, this is what we call singular solution. And in this case, we show that the singular condition, control condition doesn't exist. And it doesn't exist because of the following. You're gonna state that minus the derivative of phi second with respect to q is positive, it should be negative, and this is why it doesn't exist. But I mean, with anything you can find it that it doesn't exist. So, to obtain a better description of this potential solution, it would be helpful to study the behavior of the model, and actually also to show you how the model also work on. So by doing this, we will try to study the robustness of the model, meaning understanding which are the state and how much these trends are using. Also, we expect the appearance of an equilibrium when we go to infinity, when we change the time to infinity. So this is also something we do ask. And is it possible to have multiple solutions? Meaning have two control policies that's totally different but give us the same profit. Meaning that there is two strategies that's gonna end you with the same profit. Then you will have a problem of which strategy to choose. So the first issue is understanding the impact of the horizon time, meaning the time of working, the contract time, and the time of C, meaning the cost. Some of you will just, it's a question that anyone can ask, why we're gonna ask and we're gonna do this T and C, and where we're gonna study the sensitivity with respect to T and C. And I'm gonna take you to this function phi. And you're gonna see that phi here is equal to minus c, so it has a really dependence of c, lambda 1, lambda 2. Don't forget that lambda 1 in capital T equal to 0, lambda 2 in capital T is equal to 0, meaning that phi capital T, this disappears and this disappears, and we have minus c. So phi capital T is equal to minus c, meaning that in the end of time, phi capital T is negative, so q capital T is 0, meaning that we should end the activity by doing nothing. At least we should end the activity by, as we mentioned early retirement. But what happened previously? This is why we said that capital T plays an important role, and also C as the cost function plays an important role with phi. Either it goes, because it goes between 1 and 0, and how much it's gonna, because if you have a huge cost, like your cost is a lot bigger, then minus c is a lot lower. You see, it's difficult to get it positive, and vice versa. If it's close to 0, then anything other than that will rise it up before to 1. And yeah, so we're gonna study the impact of T and C, and you see that almost in whole cases, like for 25 years and a cost equal to 0.95, we're always gonna notice the same one. We're gonna do nothing and invest in maximum way in the first 2 years, and then we're gonna start revaluing waste by doing a decreasing function until we reach a point of time where we do nothing, and here we have no investment possible. So it's a 3-stage structure system like we've noticed. But as you notice here, I'm going to change C, so I'm going to let T stay between 25 years, meaning the contract is 25 years, but I'm going to take a increasing cost. So the cost will go from 0.9 to 1.7. And we're going to see how much this is going to change to the system. And you're gonna see that the first time and the second time, I always will tell you the first switch time and the second switch time. So you see that the first switch time is increasing with respect to time. We had with C equal to 0.9, we had an early switch time. When we added cost, we had a late switching time, meaning we started late the activity. Compared to lower cost, we will start early the activity. However, for the second switching time, it's reversible. So when you start early, you finish late. When you start late, you finish early. So this is what we found, that C is increasing with respect to the cost. The first switching time is increasing with respect to the cost. The second switching time is decreasing with respect to cost. This is what it gives us. Just remember this. I'm gonna use my hand to just, you can see it. I'm gonna point this. So the first this is the first switching time. So it's increasing with respect to cost. And this is the second one. So it's decreasing with respect to cost. So one day we'll reach a cost where these two will collide, and we will have at the same time the switching and the two switch at the same time, meaning 0, then you switch, then 0, meaning you will not work. So potentially we're gonna reflect that probably with a certain cost, this will gonna reach a level, this gonna reach a level where we won't do any activity because it will not have any sense of doing an activity to lose money. A second point is studying the impact of capital T and how much capital T is involved. And now we change capital T from 25 to 35 years, meaning to study the influence of those of the time of the contract. And we find that it's the inverse. By increasing the time from 25 to 35 years, what we notice is that the first switching function is decreasing. You see, it's decreasing. However, the second switching time is increasing, meaning what happens is they get wider, meaning that for a certain time capital T, probably when it goes to infinity, what we'll have the first switching time will happen at time 0, the second switching time will happen at time capital T, meaning that we'll start with nothing, boom, we will continue, and we will end at the activity the last day. Meaning by having more time, you can work more time, which has more sense, to be honest. So this is what we said as an interpretation. It is clear that the first switching date is increasing with respect to C, while the second one is decreasing, and consequently the treatment period is decreasing with respect to C, while the optimal investment is increasing with respect to C. So what happened also when we choose the optimal value function and we write it with respect to time T? Like, we will draw the different profit with respect to time. And you're going to see that the profit function is slightly increasing with a bit, and here it become linear. When it become linear, mean that it's become proportional to the years that we're working on. So it's not very, honestly, it's not very interesting to study when it becomes linear, because now you can see that in 100 years, when it becomes linear, you're just gonna, in 150 years, you're just gonna win more 50 years of work. It's not very interesting to you. This is why going to T goes to infinity is not very interesting, because as I said, the two switching function will go beyond, and you will work the whole activity, meaning that your control will not be very special. It will be, you have a unique control, you start the activity and you continue working until your last day, and that's not very interesting, not very different. And you're gonna see here on it, despite the limited time to the treatment due to the agreement, we could expect numerically to highlight an optimal equilibrium indeed. So the optimal profit become linear when time goes above 50 years. So when a contract is above 50 years, it doesn't become interesting, because just the control will become working your whole 15 years and nothing this. But the thing is, this presumes the existence of an optimal equilibrium. This observation can be interpreted as the damping on investment beyond a certain period, meaning that during a certain period, you will just be working for nothing. You're just working to pay your investment, to pay the salaries of everyone. You'll not be working to make money, but just working just to finish your 50 years contract. This is why I say to you, it's not very interesting to investor. Mathematically, it's beautiful, but you should always keep in mind that investor want to make money at all time. When you tell them you just at a certain time you will be working just to pay people, he will tell you I will. Hopefully, he will. I will not work during that time. So that's why the first strategy where we showed you that there is three stages: not work, work, and not work is preferable by them. Lastly, we're gonna study the importance of what we call a special cost level, where the two switching function hits, and this special cost create what we call the confusion. It's the investor should worry should vary the optimal profit with respect now to the cost. What we found is that the there is this there is this blue line, which is the optimal profit for our control. It's decreasing with respect to the cost. The more cost it goes, the more cost. And this is the line of zero, line of profitability. And you're gonna see that in certain costs, we will hit this zero line, meaning that at a certain cost, we will start eventually losing money by working. And this is something that also very interested to investors, also very interested in a mathematical way, because this point create a non-uniqueness of the optimal control solution. And I'm going to show you this. So figure 15 highlights a critical value of C for which G star vanishes. And at this critical level, which is 2.42, the investor is indifferent. He's really indifferent. You put an investor and you just tell him you are indifferent between doing two things: a no investment policies, meaning you just gonna do nothing. You're just gonna tell us I'm gonna chill out for 25 years, not work at all, or invest with zero income, meaning he will do the activity for 25 years and end up with zero benefit. He will lose, he will gain as much as he pay on cost, meaning that he will have zero income. And this fact corresponds to a multiplicity of solutions. And also these critical levels can be seen to be a level where the technology used is very sophisticated, is very expensive, is very high tech, that it's not worth using it. So now I always like to ask people which kind of these two solutions you will go for. You will go for the no investment, meaning you do nothing and you win nothing at the end, or you work an activity for the whole 25 years and do nothing. And here when we will have the face-off between government, municipalities, and private sector investors. Government, even though you tell them you will not win money, you go for the invest with zero income, meaning that you will have an activity, you will generate an energy that you will set at a price, but you will pay people, you will create jobs, you will create a lot of things. Even though you will not gain money, but you have created an activity, you've paid a lot of people. As for an investor, he wants to make money. He doesn't care about paying people. He doesn't care about sustaining an activity. So you go for you don't invest on this activity. Just leave this activity for the government. And you're gonna see that I literally have shown, and I'm showing you now the two different control policies. This is the control policies that the government gonna use and gonna gain €0, $0 by it. At the end they will be paying people, they'll be investing a lot of money and not gaining anything. And this one is for the private sector, meaning doing nothing, investing nothing for 25 years and still ending up with the same result of winning nothing. So, as a conclusion of this part, um, how can we improve the model? How can we improve the model? There is a lot of things I can say about it because I've worked on this model for 2 years now. There is the problem of comparing energies, uh, the problem of not maximizing the profit but minimizing the costs. There's the problem of having a price that's varied with time, that's having a increase in waste level influx that's going into the waste levels. There is a lot of things we're gonna should change with the model, but by changing it to the model, it will turn the study more complex and it will add difficulties to this study. Meaning, as we always say, uh, simpler model having simpler solutions, making more complex model will give you complex study, probably complex solutions that not everyone will be interested in. So, one of the answers I always also ask is what can you suggest from the previous results? Meaning that now you have seen how, in which field the optimal control theory can help us. It can help in fishery management, it can help in epidemiology, and it can help also in waste energy, waste to energy processes. Uh, how can you suggest we can add more to this theory? I've shown you a few cases, but it helps in a lot more cases. And I will end up, this is my last slide, by telling you that the optimal control theory has many applications. I only mentioned those I was lucky to work on, either published or current works. And there's always still the dilemma between the viability theory and the optimal control theory. I always tell you that the viability theory is not my sole favorite one, just because it doesn't help you do much. It doesn't have an optimality. It doesn't help you if anything. The optimal control theory, as you can see, you've saw it in the fishery management, you've saw it in the epidemiology, you've saw it in the waste energy management. It helps a lot. In those two theories, it should not be a versus. I've made a versus there because I've been inclined to always we have been inclined to always compare these theories, viability theory, optimal control theory. To be honest, there is an end, viability theory and optimal control, because at the end they are the same face of the same coin. And I probably will end this one. Thank you for your time.